For activity 2, I changed the angle of the slope to 30 degree and the static friction coefficient to 0.18. So right now we are comparing the scenario which a car driving on a flat road compared to a road with an inclined angle. And in this case, it will be 30 degree. What the car is doing right now is that it's turning toward right. So we know that they should not have a zero acceleration. In fact, we know it should be accelerating this way so that it can make the turn. So now we can draw the free body diagram, which is the force diagram. The car is on the surface of the road, so it is going to have a normal force from the surface of the road, and it is on Earth, so we will have gravity pulling the car downward. I'll just write it as mass times gravitational constant. And because there's friction on the car, and we know that the car is going to make a right turn, which gives it an acceleration toward the right, it's going to have a friction from the tires. And because the spot that the tire touched the road is not moving, and it's not sliding against the road, so we know it's going to be static friction. We are not talking about drifting, so it's just static friction. The same thing happens here, but with some different direction. Gravity is still gravity, the same car is having the same weight, so it doesn't change. But because the road has an inclined angle, so the normal force is going to point toward the top right instead of upright. I'm going to add a bar to our normal force. So the normal force and bar represent the normal force for this inclined scenario. And for the static friction, it is going to point slightly downward because it should be parallel toward the surface that the tire touches the road. So in this case, the friction force is going to point toward this direction. Now we have our free body diagram. It's good to have a coordinate system to describe them. So let's copy paste here and choose a coordinate system in part 3. So we know that the acceleration should go toward the right of this graph because it's going to make a right turn. So in both scenarios, the acceleration should be horizontal. Therefore, it's good to choose the coordinate with a horizontal axis, and we will of course call that the y-axis. Then we will have our y-axis. So this coordinate system should work pretty good for both scenarios. Now, let's break the forces into components. In this coordinate, gravity and normal force are all in the y direction, and they should cancel each other. So they should have the same magnitude in case the car doesn't suddenly fly up or sink down. And the static friction will provide all the force for this acceleration moving toward the x direction. This is for the case with a flat road. Now for a inclined road, the gravity is still pointing downward, but the normal force should have a tilted angle with respect to the vertical dotted line, and this dashed line will have a 30-degree angle between here because we are making a 30-degree inclination. This angle and this angle should be the same because when this angle is 0, this angle becomes 0, so we know they are the same. Similarly, the frictional force will make a angle which is 30 degree with the horizontal dotted line. So when we look at the vertical component, it will be the y component will be the normal force times cosine 30 degree minus the gravity and plus the frictional force times the sine of 30 degree equals 0 because it's not going to fly up or go down. For the x component, both the normal force and friction have a x component. So it's going to be the x component of normal force plus the x component of friction equals the mass of the car times its acceleration. So these are how we break the components into two parts. Now we can write down the net force and apply Newton's second law, which we just did. So let's just copy paste everything to here. So by applying what we know about these components, we should relate the acceleration to the speed of the car. So the car is going around a corner. Let's draw the corner at this. We can fit this curve with a circle that has a radius r. So right now we can view this car as a object going in a circle with some speed v. And we know that when an object is moving with a speed v along a circular trajectory, its acceleration is going to point toward the center of the circle, and the magnitude will be v squared divided by r. So now we can relate the acceleration in both cases with the speed of the car. For the flat car, it's going to be v squared over r, and for the inclined road, let's call this velocity, let's call this speed v bar. So the acceleration in this case will be v bar squared divided by the same r because it's the same curve. Now we can describe the friction and apply some constraint. So the constraint about friction is that it should always be smaller than the normal force times the coefficient of static friction. So in this case, we can add a constraint right over here because this thing directly equals to the static friction. In the other case, it's more complicated because here we have the static friction and normal force, and let us just keep the constraint over here so that we can solve it later. So we see the inclined scenario is harder to solve, but it's doable.